Array antennas, Yagi Uda antenna, series on antennas and wave propagation, lecture number 4.13. Yagi Uda antenna is an array of several elements. In this array, one element is fed and remaining elements are parasitic. In parasitic elements, again, two types exist. One type is called reflectors, another type is called directors. Usually, the lengths of the elements in this array antenna, they are not same. This antenna is widely used for TV reception. In this session, we focus and study various aspects, important aspects pertaining to this antenna. We begin the study with a small introduction. Yagi and Uda developed this array during 1926 to 29. Yes, Uda first published the original design and operating principles of this antenna in Japanese, in the Journal of IEE of Japan. Later, in a more widely circulated and read article, one of Professor Uda's colleagues, H. Yagi, described the same radiator in English, which has been considered a classic. Basically, it is an end-fire array of linear dipoles consisting of one driven element and one or more parasitic elements. The elements are placed over a boom normal to its length and parallel to each other in a plane, and usually the antenna is mounted with the plane of dipoles horizontal at a height above the ground. This gives a small familiarity with the antenna. The boom may be wooden or metal or some non-conducting one made, let us say, with the plexiglass. The parasitic elements are made with aluminum tubing. So boom is non-conducting, whereas elements are conducting. The elements of Yagi Uda array, for that matter any array, can be divided into two categories on the basis of being fed or unfed. When fed, they are called driven elements, otherwise they are called parasitic elements. The parasitic elements of this array can be further divided into two types: reflectors, which enhance the radiation towards the driven element. This gives you a definition for a reflector. Reflector is one which enhances radiation towards driven element, and directors are elements which concentrate the radiation in a direction opposite to the driven element. Reflector in general is a body surface which can alter the path of wave in accordance with the Snell's laws of reflection. They act like mirrors. Reflectors are mirrors. At microwave frequencies, dipoles with the length slightly more than one half wavelength and some other metallic surfaces can act as reflectors effectively. Dipoles with length more than one half wavelength, they act as reflectors. Other metallic surfaces are also there, which can act as reflectors. Deflectors, on the other hand, are also body surfaces, and their interaction with the wave is similar to refraction of light through dielectrics. Deflectors are synonyms with the director. Another name for director in Yagi array is deflector. Apart from other arrangements, dipoles with length slightly less than one half wavelength can act as deflectors or directors. As already mentioned, deflector and director, these two are synonyms. While transmitting, the driving elements get energized by conductive coupling, whereas parasitic elements get energized by mutual inductive coupling. In Agi, only one driven element exists. It is a half wave dipole. This element gets energized by conductive coupling, whereas all other elements of the antenna, they get their energy through inductive coupling. And the parasitic elements of the array are elements which are connected not directly to the source in case of transmitting antenna, to the receiver in case of receiving antenna. Here the point is, parasitic elements by definition are elements of the array which are not connected directly to the source when it is acting as a transmitting antenna, to the receiver when it is working in receiving mode. A driven element can be defined as one which is connected directly or conductively to the transmitter in case of transmitting array, to the receiver in case of receiving array. Here, definitions of parasitic elements and driven elements are being given. The Agi has only one driven element, half wave folded dipole, only one reflector, but several director elements, deflector elements. Linear dipoles whose length is slightly less than resonant length are used as deflectors or directors, whereas linear dipoles whose lengths are larger than resonant length are used as reflectors. Reflector dipole can be viewed as an opened out parallel wire transmission line with a length slightly more than a quarter wave length, which is equivalent to a pure inductor. Hence, reflectors carry inductive currents when excited. Similarly, director dipoles carry capacitive currents. The equivalent circuit of a quarter wave transmission line is a series LC resonant circuit, and hence half wave dipole driven element carries resonant current. Some more points regarding Yagi. The reflector carries inductive or lagging currents, driven element carries in-phase currents, whereas directors carry capacitive or leading currents. Hence, it can be concluded there exists a traveling wave current along length of the array, even though its amplitude and phase progression is not uniform. In general, the phase shift and phase velocity of the traveling wave in Yagi Uda array structure is controlled by the geometrical dimensions of the array and its elements, and it is not uniform from element to element. Here, the point is this: it is an array consisting of resonant elements. Half wave dipole is a resonant, one, reflectors, directors, or deflectors are also resonant ones. So we may be tempted to think that it is a resonant antenna, but there is a view which can show this antenna as a traveling wave radiator, traveling wave antenna, non-resonant antenna. That view is described, justified here in this particular slide. Complete info, mechanical structure as well as electrical characteristics. They are given in a tree diagram in this slide. Name is Yagi Uda Array. Radiation is end fire 1. Gain is moderately high. It is roughly 6L over lambda. Lambda is wavelength, L is length of the array. Lightweight, low cost are its mechanical characteristics. Relatively narrow banded antenna. This one popular at HF, VHF, UHF. In earlier days, it was used as receiving antenna for terrestrial TV broadcasting network. As already mentioned, it consists of two types of elements. Driven element is one, only one. Parasitic elements, there are several. Driven element is one, as already mentioned, which is directly fed. Whereas parasitic elements are elements which are inductively fed. Conductively or directly fed is driven element, whereas inductively fed is parasitic element. In parasitic elements, again two types: reflectors, directors. Reflector is one, only one. Directors are several. Why only one reflector is used in Yagi? Reason is, even if we go for more than one reflector in the design, it doesn't give much benefit. The benefit we get by going more number of reflectors is quite insignificant. So the number of reflectors is limited to one. Directors are several. It is found that more number of directors, they give more gain. Now, some points regarding driven element. Folded dipole with length equal to its resonant length in the absence of parasitic elements is used as driven element. Its length is 0.48 lambda. It is not 0.5 lambda. Input impedance of a driven element is 300 ohms. It carries a resonant current. Some aspects pertaining to reflector. It is dipole with the length equal to 0.49 lambda. It controls driving point impedance and back lobe. It carries inductive current. Spacing is 0.25 lambda. Now some points regarding directors. Dipole with length 10 to 20% shorter than their resonant length. This is the physical dimensions of directors. Roughly it is 0.45 lambda. Controls gain and pattern shape. Carries capacitive current. Spacing is 0.3 lambda. Here is shown the array, Yagi Uda array, driven element. Input impedance of element is 300 ohms. Here is a reflector. Here are directors. Only one reflector. Spacings are given here. 0.25 lambda, 0.31 lambda, 0.31 lambda, 0.31 lambda, 0.31. Here is metal boom. This is metal boom. These are all directors. Feeding is given directly to the dipole, folded dipole. Radiation is towards director. Functioning. The driven element, when connected to the source, starts radiating. When this radiation falls over the parasitic elements, they get excited, resulting in the time varying currents over them. The excited time varying currents of the parasitic elements start radiating. The net result is all the elements, whether driven or parasitic, start radiating. The spacing and sizes of the elements are selected in such a way that radiation from different elements cancel each other as nearly as possible in the direction of reflector, and radiation from the elements add to each other, giving maximum radiation in the direction of directors or deflectors. So there exists maximum radiation towards directors and very little or nil radiation towards reflector. Tuning and bandwidth. The antenna can be tuned either by inserting a lumped reactance in series with the antenna at its center point or by adjusting the length of the parasitic elements. What is tuning? Changing the frequency of operation of the antenna. How to change its frequency of operation? It is done through a mechanism called tuning. Here, two methods are described: by inserting a lumped reactance or by adjusting length of the parasitic element. It is a relatively broadband because folded dipole with a typical value of 15%. Bandwidth is 15%, and the broadbandedness of this antenna is the result of a folded dipole. Ordinary dipoles, they are not broad banded, but folded dipole, it exhibits broadband characteristics. Presence of folded dipole in the structure of a Yagi Uda array, it gives rise to broadband characteristic to the array. The bandwidth can be further increased by lengthening the reflector and shortening the directors, but at the cost of the gain. Now, radiation characteristics. Ag exhibits a highly useful radiation characteristics. The salient features of this pattern are: 1. It has a quite good unidirectional radiation pattern. The main beam is along the axis from director to reflectors. Small correction, it is from reflector to director. Back lobe exists, but it can be made insignificant by proper design. Second point, its polarization is linear. If the dipoles are along z-axis, the E vector is in polar theta direction. Third one is it can be used to produce circular polarization. Two Yagi Uda arrays are placed with their dipoles at right angles on the same beam, with the driven elements being fed in phase quadrature, or both the driven elements being fed in phase, but with one array displaced lambda by 4 along the boom with respect to the other to produce circular polarization. These are two techniques by which one can generate circular polarization from two Yagi arrays. Some more points regarding radiation characteristics. Fourth point, there exists unwanted side lobes or minor lobes indicating radiation in unwanted directions. The minor lobe level is minus 5.23 dB or smaller. Fifth point, it is an antenna with moderate gain, and the gain can be related to its length through 6L by lambda. L is length. The gain can be increased either by increasing the length of the array, by adding more directors, Twice the gain requires a four-fold increase in length, or by stacking two arrays. These are two methods by which one can have more gain from Aggie. Here is antenna. This is a reflector. These are all directors. Driven element. Now this is the main lobe. These are side lobes. So pattern is shown in relation to antenna in this slide. Design. The standard procedure uses the extensive data available from several experimental investigations carried out by NBS of US. It is a three-step procedure. First, approximate dimensions are found, then optimized dimensions, at the end compensated dimension. In the first step, that is in finding approximate dimensions, the data available from the above mentioned source, antenna parameters like lengths and spacing of the elements are determined. In the second step, optimized dimensions are determined using curves available from the same source. The lengths of the parasitic elements are optimized for their finite diameter. In the last step, that is determination of compensated dimensions, the lengths of the elements are compensated for finite boom diameter. However, the procedure that is mentioned in the previous slide, it is somewhat laborious. If the requirement is a simple and fast design, then the formula given here can be used. When the requirement is a simple fast, the following formula can be used, which however are able to give only approximate dimensions. In this formula, frequency is in megahertz. Length of the driven element, it is 0.48 lambda. It turns out to be 144 over f meters. Length of reflector, 0.49 lambda. It turns out to be 147 over f meters. Length of directors is 135 over frequency f meters. Reflector spacing is 0.25 lambda. It is equal to 75 over f meters. Director spacing is 90 over f meters. As already mentioned, these are simple formulas, but they don't give exact dimensions. They are approximate. We spend some time on merits, demerits, application. Merits. One, lightweight. Usually aluminum tubes are used to make driven element, director and reflectors, which are of lightweight. Two, simple construction and easy design. It does not require much technical knowledge to design or technology to fabricate the antenna. Three, low cost. Aluminum tubes and iron beam does not cost much. Four, provides moderately desirable characteristic. Gain is not low, radiation is unidirectional and side lobes are negligible. Applications. 1. It is a traveling wave antenna used in the HF, VHF, UHF ranges. 2. It is widely used for transmission in HF range and for TV reception in VHF range. Here is shown and described a variant of Yagi. It is called Landsdorfer array. It is derivative of Yagi array by extending and shaping the conductors as shown below. Here is a director, here is a reflector, this is a driven element. The shapes are different. Its pattern is also shown here, field pattern. With this, we come to an end to this session. This session is mainly focused on introducing Yagi Uda array and also describing its properties. its structure, its electrical characteristics, its merits, its applications. So, hope this session is useful to you. We meet again in another session later with a new topic.